Welcome to The Explainer. Look, if you're a focused learner aiming to absolutely master the Cambridge IGCSE additional mathematics syllabus, specifically code 0606, you are exactly where you need to be today. Today, we're not just doing a standard math review. No, we are completely opening up the examiner's playbook. I want you to think of this like you are stepping into a corporate boardroom. Your examiner is the CEO, and you are the lead strategist pitching your mathematical solutions. Every single point needs to be justified with solid data and a flawless strategy. We're going to take an insider's look at one of the most vital, yet frankly most frequently misunderstood areas of the entire math syllabus, understanding integration as the reverse process of differentiation. We aren't just memorizing formulas today. Anyone can do that. We are breaking down the exact mechanics of how you are graded, how those examiners actually think when they see your paper, and how you can systematically secure those top marks every single time.
Okay, let's dive right into this roadmap. We'll start with the 15% secret, move into the core theoretical foundations, break down the procedural framework, elevate your critical analysis skills, and finally, reveal the top examiner warnings.
Let's kick things off with Section 1, the 15% secret. This is absolutely crucial.
Before we even touch the how of integration, we desperately need to talk about the why. Why are we hyper-focusing on this? Well, what's incredibly interesting, and honestly kind of shocking for a lot of students, is the sheer weight of this single topic. Integration, as the reverse process of differentiation, doesn't just represent a handful of stray marks you can afford to lose. No. It accounts for approximately 15% of the total marks in your additional mathematics examination. Let that sink in for a second. Out of the entire massive syllabus, mastering this one interconnected concept is the equivalent of securing a foundational chunk of your final grade. It is literally the difference between an average grade and a top-tier result. Whether you are dealing with syllabus 0606 or looking at the broader calculus concepts across 0580, 4024, 4037, or 4040, this logic holds up. You simply cannot afford to gloss over it. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
And listen, this isn't just some random statistic we pulled out of thin air to scare you. This is a direct quote from a Cambridge senior examiner. When the very people who are writing and grading your papers highlight a specific percentage like this, you need to treat it like a neon sign pointing directly at a strategic necessity. It completely proves that having a deep, mechanical understanding of how integration reverses differentiation is exactly what separates the elite candidates from the rest of the pack. It tells us that the board isn't just looking for lucky guesses, they want to see your strategy on paper.
Moving on to Section 2. Let's build out those core theoretical foundations. To actually secure that 15%, we have to meet the academic benchmarks set by the board. Here is the formal definition you need to completely internalize. Integration as reverse differentiation is a conceptual framework relying on systematic analysis and evidence-based reasoning to reverse a derivative back to its original function. Notice the exact phrasing there. It doesn't say guessing the antiderivative. It says systematic analysis and evidence-based reasoning. Think about a concrete example, like kinematics. If you differentiate displacement to find velocity, reversing that process, meaning integrating that velocity to find displacement, requires you to prove step by step that you understand the mathematical relationship going backward. The examiners are explicitly looking for that proof in your pitch. They want the evidence, not just your ability to memorize a single calculus rule.
This brings us perfectly to the assessment objectives, which target three distinct cognitive domains: knowledge and understanding, application, and analysis. This is precisely why multi-stage calculus analysis often totally derails students. Imagine a student, let's call him Alex. Alex overloads his answers with raw mathematical facts, but provides absolutely no analysis. He shows he has knowledge, but fails the other two. Then you have Sam. Sam rushes through the paper, completely misses the command word requirements, and messes up the application. It's not enough to just know the integration rule. You have to apply it to complex, multi-layered problems and then critically analyze the result to ensure it correctly reverses the differentiation given in the prompt. You are being tested on all three of these levels simultaneously, and dropping the ball on any of them costs you marks.
So, how do we fix that? Let's look at Section 3, the procedural framework.
To systematically tackle these problems and beat the Alex and Sam trap, you must utilize the method mark strategy. Guys, this is an absolute game changer. Examiners award points for your process, not just your final answer. In the high-pressure environment of an exam, you might make a tiny, silly arithmetic error at the very end of a complex integration problem. If you only provide the final number, you get slapped with a 0.
But if you clearly document your systematic processing, if you lay out your mathematical pitch step by step, you bank valuable method marks every single step of the way. Your process is your ultimate safety net. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
To maximize those method marks, you must follow this strict 5-step execution framework. Step 1. Deconstruct the question. What exactly is the command word asking you to reverse? Step 2. Extract the relevant data from texts, graphs, or tables. Step 3. Select your analytical framework and execute the integration with perfectly clear notation. Think of this as the math version of the Peel framework. Make your point, show your evidence through working, explain the steps via notation, and link it back to the derivative. Step 4. Verify your results. And finally, Step 5. Present your final answer using the correct mathematical terminology. If you follow this chronological sequence, you leave absolutely no marks on the table. It is a foolproof system.
And speaking of that final step, presentation, there are strict conventions you must follow. We're talking proper headings, correct terminology, appropriate formats, and incredibly clear annotation. Listen to me on this. Presentation is not an optional bonus. It is a strict requirement to extract data and draw evidence-based conclusions properly. If your working is scattered all over the page like a messy brainstorming session, without clear annotation linking your integration steps back to the original derivative, the examiner literally cannot award you those method marks. Structure is everything when you're pitching your answer to the board.
All right, let's level up. Section 4. Critical Analysis Skills.
To elevate your answers from basic to truly exceptional, we need to move into the higher order assessment objectives. This framework breaks down into 3 very distinct levels. An average student stays right at the descriptive level. They just identify basic similarities and differences in the math. Good students push up to the analytical level, supporting their integration steps with solid evidence and logical flow. But the top-tier students, the ones securing that full 15%, they reach the evaluative level. They evaluate alternative approaches to the integration, they understand the limitations of the data provided, and they fiercely justify their mathematical recommendations. This is exactly what the Cambridge syllabus benchmarks demand for those elusive top grades.
To actually reach that evaluative level, you must deeply understand how to evaluate the quality of your mathematical evidence. This isn't just crunching numbers. It requires identifying limitations in the given data. It requires acknowledging any assumptions made during your integration process. For instance, assuming a constant of integration in a kinematics problem where initial conditions aren't perfectly clear. You have to consider alternative interpretations of the equations, and most importantly, you have to understand the effect of all these factors on your final conclusion. This is what proves to an examiner that you aren't just a calculator. It proves you are thinking mathematically and strategically.
Finally, let's look at Section 5, Top Examiner Warnings. This is the stuff that trips everyone up.
Consider this an insider leak straight from the principal examiner reports. There is a massive glowing disconnect between what candidates do and what examiners actually expect. Look at the typical student. They give vague answers, they completely forget formatting, and they ignore the context. It's the classic Alex and Sam scenario all over again, either rushing and missing the point or dumping irrelevant facts. Conversely, examiners are sitting in that boardroom demanding specific details, strict adherence to presentation conventions, and answers that are explicitly tied to the context provided in the prompt. If the question involves a real-world application, your integration must reflect that specific real-world context, not just a bunch of abstract floating numbers.
I need you to pay extremely close attention to this examiner alert. The reports consistently highlight that candidates wildly confuse key terminology when discussing integration and differentiation. This is a massive red flag that will tank your grade. The directive here is crystal clear. Always define your terms before using them in extended mathematical responses. If you are applying a specific calculus rule to reverse a derivative, explicitly state what you're doing. If you add a plus c, know what that constant represents in your specific scenario. Clear terminology demonstrates a clear, undeniable understanding.
To help you avoid these exact pitfalls, here is a highly effective, source-derived memory hack you can use right now. Use a visual story method to encode these integration concepts. Instead of just staring at a dry formula until your eyes glaze over, visualize the process. Picture the derivative as a physical object that has been broken down into pieces, and treat integration as the systematic, step-by-step physical process of rebuilding it back to its original perfect form. Linking these abstract mathematical processes to visual, sequential stories helps lock them firmly into your long-term memory so they are ready to go on exam day.
All right, we've covered the high stakes, the theory, the strict procedural framework, the critical analysis, and the major examiner pitfalls. Now the execution is entirely in your hands. Which of the 5 procedural steps will you focus on during your next past paper practice to secure your 15%? Are you going to focus on decoding the command words, or perhaps verifying your results at the very end? Think about your weakest link, apply this examiner's playbook, and start practicing with serious intention. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.